Hello everyone. Let us continue the second part of today's class. Okay, let us continue to see the handout. Okay. In other words, a monoid is a semigroup. Okay, we will introduce what is a semigroup later. With an identity element. It can also be thought of as a magma. Okay, we will introduce what is a magma later. With associativity and identity. The identity element of a monoid is unique. Okay. For this reason, the identity is regarded as a constant, that is, zero area or nullary operation. The monoid therefore is characterized by specification of the triple S. Okay, do you remember what is S? Okay, where is S is the set. Okay, that we consider. Okay, and the dot is the operation we consider. And E is the identity element that we consider. Okay. Depending on the context, the symbol for the binary operation may be omitted so that the operation is denoted by juxtaposition. For example, the monoid axioms may be written AB parenthesis C is equal to A parenthesis BC, and EA is equal to AE is equal to A. Okay. This notation does not imply that it is numbers being multiplied. Okay. A monoid in which each element has an inverse is a group. Okay, we have introduced what is a group. Okay, earlier. If you forget it, please review it. Okay, let us see an example. The set of natural numbers n, which is equal to 0, 1, 2 dots. Okay. Please note that some books define the natural numbers n without the element 0. Okay, here we consider the element 0. Okay, it depends. It's a commutative monoid under addition. Okay, the identity element is 0. Or multiplication, the identity element is 1. Okay. So this 0 is called the additive identity, and 1 is called the multiplicative identity, as we have mentioned before. Okay, a submonoid of n under addition is called a numerical monoid. Okay, next, let us see problem 14. What is a semigroup? Okay, why do we need to know what is a semigroup? Okay, this is because we have mentioned it before. Okay, let us find it out. Okay, semigroup. Okay, so here we have mentioned set the proper noun semigroup. Okay, which is in the solution to problem 13. What is a monoid? Okay, let us go to semigroup. Okay, the definition of semigroup is relative simple. Let us see the definition of a semigroup. Okay, a semigroup is a set S together with a binary operation dot that is a function dot from s times s to s. Okay, here means times means the Cartesian product, and I will introduce it later. Okay, that satisfies the associative property. Okay, for all a, b, c in S, the equation parenthesis a dot b dot c is equal to a dot parenthesis b dot c holds. Okay, that is, if we want to compute a dot b dot c, then we can compute a dot b first, then dot with c. Or we can also compute b dot c first and compute a dot parenthesis b dot c. Okay, the result of the both sides of this equation are equal to each other. Okay, more succinctly, what is succinctly? Succinctly. Okay, that is, you say something in a short way. This means the succinctly. Okay, a semigroup is an associative magma. Okay, we will introduce what is a magma later. Okay, example, empty semigroup. Okay, this is the most simple example of a semigroup. The empty set forms a semigroup with the empty function as the binary operation. Okay, we will introduce what is the empty function later. Okay, so next, there are also many problems here on page 53. Okay, from problem 15, what is a magma? Okay, to the problem 23, what is a binary code? Okay, the solution to these problems is still under preparation. So please let me introduce the solution to this problem in the next class. Okay, so let us go back to the progress. Okay, let us see. Okay, we have finished introduce handout page 53. Okay, the problems with solution. Then let us go back. Okay, this is from the chapter 3 slides, page 53. Okay, maximum likelihood. And before introduce the maximum likelihood, we have taught to chapter 3. Okay, here chapter 3 slides 103. Okay, so please open the slides of chapter 3. Okay, and please turn to the page 103. Okay, we are talking the single mode eigenbeing. Okay, to see this, okay, to see what, let us go to the previous page. Okay, the answer is that it enables higher throughput than can be achieved with a SISO system at the same signal to noise ratio. Okay, here is an answer, so there must be a question before the answer. Okay, let us see. One might ask, what benefit is there in only transmitting data using one eigenmode? Okay, that is, it is single mode eigenbeing. Okay, let us go back to page 103. Okay, so C single mode, it is the capacity of a MIMO system that uses single mode eigenbeing is equal to log 2 of 1 plus rho 1. Okay, what is rho 1? Let us review it. Okay, please see the previous slides. Okay, and search for row 1. Okay, it is important for you to learn to review the old knowledge before you learn the new knowledge. Okay, row 1. Okay, here is the row I. Okay, so row 1 is row I for I is equal to 1. That is the received SNR in the ith eigenchannel. Okay, let us go back to page 103. Okay, and it is equal to log 2 of 1 plus row P1 lambda 1. Okay, do you remember what is row? Okay, let us review what is the meaning of row. Okay, let me change the pointer to a laser point. Okay, let us search for the definition of row. Okay, here is the row. It means signal to noise ratio. Okay, but it is not the most detailed definition. Okay, we need to find the detailed definition. Okay, row. Okay, let us find the definition of row. Okay, here row means the signal to noise ratio. However, it is not the detailed definition. Let's find the detailed definition of row. Okay, row is the signal to noise power ratio at the receiver. Okay, it is page 7. Okay, let us go back to page 103. Okay, and the row times P1. Okay, what is the meaning of P1? Okay, let us go back to find the definition of P1. Okay, on page 65, Pi is defined as the expectation of the square of the absolute value of S tilde I, where I is equal to 1 to R. Okay, the R is the channel rank. Oh, here is an error. Let me fix it. Okay, the number of the equation should be aligned to the right. Okay. Okay, good. Okay, then what is the definition of S tilde I? Let us review it. Okay, S tilde I. Okay, on page 46, S tilde. Okay, S tilde is the, we can see that assume that at some instant the transmitter has R symbols to transmit. S tilde is defined as S tilde 1 to S tilde R transpose. So S tilde 1 is the first symbol to transmit at the transmitter at some instant. Okay, let us go back to page 103. Okay, and P1 times lambda 1. Okay, what is the definition of lambda 1? Okay, let us go back to the previous slides to find the definition of lambda 1. Okay, it should be in the SVD, that is a singular value decomposition. Okay, we are getting close. Okay, so D, okay, the matrix D comes from the singular value decomposition of H. So H is equal to U times D times V Hermitian. And the diagonal elements of D is equal to square root of lambda 1, square root of lambda 2 to square root of lambda R. Okay, so lambda 1 is the largest eigenvalue of H times H Hermitian, where H is the channel matrix. Excuse me. Okay, so let us go to page 103. Okay, I need to fix this error. Okay, equation 3.27. Okay, and align to the right. Okay, good. Okay, which follows from equation 3.27. Okay, let us go to equation 3.27. Okay, in equation 3.27, we can see that CEIG, that is the capacity with eigenbeamforming, is equal to summation I is equal to 1 to R log 2 1 plus rho I. Okay, rho I is here, and it is equal to summation I is equal to 1 to R log 2 of 1 plus rho times the expectation of the square of the absolute value of S tilde I times lambda I. Because we are talking about the single mode eigenbeamforming, so we only use the first mode, that is, we only consider the term I is equal to 1. Okay, so we only have this term with I being equal to 1. Oh, here is another error. Okay, 3.27. Okay, let us go back to page 103. Okay, we have finished introduced this page. So, okay, next page, since summation IPI is equal to 1. Okay, let me change the pointer. This implies that in the single eigenmode case, P1 is equal to 1. Okay. The capacity therefore reduces to C single mode is equal to log 2 of 1 plus rho lambda 1. Oops, okay, here is another errors. Okay. Okay, so we can see that from the previous slides. Okay, P1 is equal to 1, so P1 can be cancelled. So the remaining term is log 2 of 1 plus rho times lambda 1. Okay. Recall that in general, summation I lambda I is equal to the square of the Frobenius norm of the channel matrix H. Okay. And for the type of normalization used in equation 3.21, okay, let us go to equation 3.21. Okay, in equation 3.21, oops, there is also an arrow here. Okay, let me fix this arrow. Okay, 3.21, not in boldface. Okay, good. Okay, in equation 3.21, okay, let me change the pointer. The received signal vector is given by R, which is equal to the square root of rho. Okay, where rho denotes the total power received at each receive antenna from all the transmit antennas, divided by the thermal noise power at each receiver, okay, times H, where H is the channel matrix, then times S, where S is the transmitted signal vector, and plus Z, where Z is the noise vector. And because S is equal to V times S tilde, okay, what is the matrix V? Okay, it is also related to the singular value decomposition. Okay, let us go to previous slides. Okay, in the singular value decomposition, H can be written as U times D times V Hermitian. Okay, where V is a unitary matrix. Okay, let us go back to equation 3.21. So the received signal, a signal vector R, can be rewritten as the square root of rho times H times V times S tilde plus Z. Okay, let us go back to page 105. Okay. It follows that the Frobenius norm, the square of the Frobenius norm of H is equal to Nt times Nr. Okay, why does this equal to Nt times Nr? Okay, because it comes from the very early equations. Okay, here. Oops. Okay, the equation 3.3. Okay, let me fix the arrow. Okay, I do not know one thing. Okay, if you know the answer, please tell me. Okay, in the PowerPoint, I am using Microsoft 365. Okay, if we excuse me. If I align the equation number of an equation to the right, and I save this file and close this file and open this file again. Okay, and the equation number will just to the right of the equation. Okay, not align to the rightmost. Align to the right margin. Okay, if you know how to fix this problem, okay, please tell me, and I will be very appreciated. Okay, so in equation 3.3, we can know that the square of the Frobenius norm of H prime is equal to Nr times Nt. Okay, Nr is the number of received antennas, and Nt is the number of transmit antennas for fixed H prime. Okay, let us go back to page 105. Okay, let me change the pointer. Okay, it is 25 minutes. Let us take a break.